Hello everyone. Here is a 5-minute presentation for our paper When Noisy Label Meets on Long-Tail Dilemmas of Representation Calibration Method. I'm Xuyang Zhao. This is a joint work with Man Yizhang, Junyao, Chunyuan, and Weiran Huang. Now let's begin formally. The success of deep learning relies on large-scale and high-quality data sets. However, real-world tasks are usually imperfect. For example, there could exist some incorrect annotations, and the sample size of different classes could be imbalanced. Reality even be more complex. The class imbalance and noisy label could exist simultaneously. Existing methods usually focus on addressing either noisy label or class imbalance separately. Methods designed for noisy label problem usually cannot distinguish tail class data and noisy label data. For long-tail problem, most of the algorithms assume that the labels are correct and suffer from mislabeling. Existing methods to tackle these two issues simultaneously usually lack theoretical guarantee, rely on strong assumptions, or have unsatisfactory experimental results. In this work, we propose a method that uses contractive learning and further calibration to address both of these issues simultaneously. We name our method as SAL. Our approach consists of three parts: contractive learning, distributional calibration, and further fine-tuning. In the first step, contractive learning is employed for pre-training to obtain a representation, which can capture similar features within the same class and learn discriminative features between different classes. The advantage of contractive learning is that it will not be influenced by noisy labels. Besides, its learned features could exhibit clustering properties. After contractive pre-training, we then conduct some distributional calibration to elevate the noisy label and long-tail issues. Our approach here is based on the assumption that before contamination, the deep representation learned by contractive learning for each class approximately follows a Gaussian distribution. This is observed by other works. Based on this assumption, we can estimate the mean and covariance matrix of each class for the following calibration. Specifically, we first use an outlier detection algorithm, LOIF, on data representations to identify potentially incorrect annotation data and remove them. Then, we can estimate the mean and covariance matrix for each class. For two classes whose sample size is small, we further use the information of head classes which are close to them to help their estimation. After estimation, we resample some data points on these Gaussian distributions to elevate class imbalance. In the final step, we further fine-tune the learned representations and train a final classifier using the calibrated dataset. We use the distance from original representation as a regularization term to keep the knowledge learned by contractive learning. And the final objective function is the cross entropy evaluated on calibrated site plus the regularization term. The overall algorithm flow of our method is shown below. Next, we present some of our experimental results. We first tested the performance on simulated CIFAR 10 and CIFAR 100 with different imbalance ratio and noise rates. In almost all scenarios, our method performed best, especially on hard settings where both imbalance ratio and noise rates are both large. Our method improves the other method most. We also conduct experiments on web vision, ImageNet, and clothing 1.9, and found our method also performed best. We also test sensitivity with respect to the network hyperparameters and do some ablation experiments. We found that each module of our methods has its own contribution to the final performance, which is more significant in harder settings. Finally, we conduct TSN evaluation on the features trained by SAL and ERM. Clearly, the features obtained by SAL have better clustering performance. We also report the effect of batch size. That's all. Thanks for listening.